Second, welcome to GAN course on advance in enhanced oil recovery in the shale and tight reservoirs, opportunities and challenges. So today, I will discuss some fundamentals of chemical enhanced oil recovery. Though this is focused for shale, oil and tight reservoirs, but it is equally applicable to general type of, or that is conventional types of reservoirs also. So my whatever the numerical problems and subsequent discussion, that will be based on the fundamentals of enhanced oil recovery. Now, starting with polymer, as I had mentioned earlier, that injection of the polymer is a great challenge for shale or tight reservoirs, though our ultimate target or ultimate mechanism for this enhanced oil recovery to improve the viscosity of the injected fluid, that is polymer. But your viscosity should not be very high, so that the injection may be a problem, or there may be, if we basically inject at high pressure, there may be the formation damage, and that is not expected. Now, the rheological behavior of a polymer solution is basically expressed by some fundamental law, that is the power law model. Now, this is the typically power law model for Newtonian fluid. And here you can see that there are two parameters are there. One is the K, that is the consistency of the fluid, and N is the flow behavior index. Now, if the value of N equal to 1, then obvious, and then K will be equal to mu, then your case is the Newtonian fluid. And if the values of N not equal to 1, that is if it is less than 1, then it will be a shear thinning pseudoplastic fluid. And if the N is greater than 1, then these values, then it will be shear thickening, and this type of fluid is known as the dilatant fluid. Now it is observed that in the most of the cases, that is the polymer what we are using in the enhanced oil recovery to improve the mobility ratio is generally shear thinning fluid, where the values of N is less than 1, and it is the pseudoplastic fluid. And this particular, in this case, these two parameters, that is the K value and N value, is very important, particularly when you will be going for the simulation study, where the because you know that I will show in the next slide. Particularly here you can see that we can rearrange that equation in this form. That is tau equal to K shear rate to the power n minus 1 into shear rate. And this is basically known as the apparent viscosity. Now, if we know the values of K and N, we can get the values of apparent viscosity at a particular shear rate. And that input is sometimes required for the simulation studies when you are incorporating the term of improvement of mobility ratio, and you have already gone through that how this mobility ratio improved the aerial or vertical sweep efficiency. Obviously, if the apparent viscosity or mobility ratio is less than 1, then your sweep efficiency will be significantly higher. Now, this power law model can be expressed if we take the log on the both side. Log on the both side, then you can take that is the log of tau, that is the shear stress, equal to log of k plus that is I am talking about the this equation, that is the common fundamental equation of the power law model. If you take both side log, then you will get log of tau equal to log of k plus n log of tau. Then if we plot this log of tau versus log of shear rate gamma, then from the intercept you will get this is the log k is nothing but the intercept and n is the slope. So from the intercept you can get the values of k, that is the consistency of the fluid, and n you can get, that is the flow behavior index you can get from the slope. And these are the different types of behavior, that is the say Newtonian fluid, pseudoplastic fluid, dilatant fluid, and plastic fluid. And there is another parameter, particularly when we are talking about the shale gas, shale oil or tight reservoir. And if we compare it with the conventional oil and gas reservoir, where the permeability or porosity is significantly high compared to the shale or tight reservoir, then this molecular weight of the polymer plays a very important role. This molecular weight is related to the viscosity. And as I mentioned, that the viscosity should not be much higher, then you have to design, that is some tailor-made polymers are required that you may synthesize or you may design, you may develop. So in that context, there is a one equation that basically Mark Howink and Sakurada, that is MHS equation, is used, which basically relates the viscosity, that is the apparent viscosity, to the molecular weight of the polymer, and where this tau is the polymer's intrinsic viscosity, and k dash is a parameter. K dash is a parameter, and alpha is also another parameter. Okay, and this particular parameter for a particular solvent system is known. For example, for most of the solvent, this alpha is generally equal to 0.8, and for good solvent, it is, say, for example, water, it is 0.8. And this k dash value is also basically known if we perform some experimental studies with some known polymer, that is the known polymer with the known molecular weight, and measure their viscosity, will get the values of k dash. And then if the k dash and alpha is known, if this alpha and k dash is known, then if you develop or synthesize a certain molecular weight, you can get their viscosity. Or other hand, if you basically fix the viscosity, that I want this particular, say, 100 millipascal second viscosity, then accordingly, what will be the molecular weight of the polymer that basically you can develop accordingly so that it can be applied for that specific field. Now, here it is a typical problem, say determine the consistency index, that is the K value, and power law index, that is our flow behavior index, using the power law model from this rheological data. Now, this rheological data of a polymer is measured by rheometer, where you can get the values of different values of the shear stress for different values of the shear rate. So these are the data, these are the different shear rate data, and this is the corresponding shear stress data. Okay, now as per earlier discussion, that is if you take the log on both sides, so this is the again the same data, then we have taken the logarithmic of the shear rate and this log of shear stress. Okay, now if we plot it, that is here, that is you can see that log of shear rate and log of shear stress, then you can see that it is a straight line, and this is the intercept. This particular value is the intercept, and this is the slope. And if you from the plot in the Excel, you can get the corresponding equation also, where you can see that slope is 0.695 and intercept is 1.7646. So here this n value, obviously it is you can see 0.96952, that is less than 1, and it is so shear thinning pseudoplastic fluid, and the C value, that is according to this equation, C value is the log of K, and you can get the K value. So K is 58.157. Now, if you are asked to calculate because our prime concern is that how to calculate the shear, how to calculate the apparent viscosity at a particular shear rate, because you know that when this polymer is injected into the reservoir, its shear rate may vary widely, particularly for the injection point where the flow area relatively less, their shear rate will be high, and when it will be entering into the reservoir, that is the porous media having significant large area, there the shear rate value will be much less. Say generally it varies from 2 to 10 second inverse shear rate. So now if you are asked that to calculate the apparent viscosity at 2.5 second inverse shear rate, okay, then you can basically you can easily get this value, particularly in this equation. If we put this is the apparent viscosity equal to this K into shear rate to the power n minus 1, and if your K value is known and n value is known, so you can get this apparent viscosity much easily. So this it's just a relationship between polymer viscosity. Now coming to the surfactant, as we know that surfactants are used to reduce mainly the interfacial tension, and when you are adding the surfactant to the some say aqueous media, that is in water, what happens? These surfactants are first you can say that here this particular say you have taken simple water, there is no surfactant is there. Then when you are adding surfactant, you can see that surfactant are adsorbed at the interface. Surfactant are adsorbed at the interface, and it basically reduces the surface energy, and subsequently the surface tension value reduces. And then at a time this you can see that this total surface is basically saturated by the surfactant solution, the surfactant molecule. And when that is the minimum surface energy you can get, because after that no further adsorption is there. So that particular point is known as the critical micelle concentration, or CMC. Now the CMC measurement is very important for surfactant flooding, because anyway, as our intention is to minimize the surface tension or interfacial tension, so you have to maintain the CMC value. Rather, in the actual case, when you are injecting the surfactant solution into the formation, to reduce the interfacial tension or solubility alteration or emulsification, generally the surfactant concentration should be higher than the CMC values. Why? Because some surfactants are lost due to absorption. And then what happens if you use the concentration as a CMC, that is the critical micelle concentration, then by adsorption, the some portion of the some amount of the surfactant will be absorbed on the rock surface and lost. And then what happened? The concentration will be reduced, and then you will say for this particular, then you will get a much less values of the surface tension or interfacial tension. So that is not desired. So accordingly, you have to perform some study, that is the adsorption. What is the adsorption for particularly in the shale or tight reservoir? There is significant amount of clay is there, and this clay are very basically sensitive to the adsorption of the surfactant because of their some active sites and different mineralogy, and therefore you have to keep it higher than, according to if you perform the absorption study, then you can design whether your injected concentration should be sometimes it's maybe 1.5 times of CMC, sometimes it's maybe 2 times of the CMC. So accordingly, you have to take the decision. And so for that, you have to know that how do you measure the surface, this critical micelle concentration. So for that, the simple study, there are tensiometer is there. So tensiometer, you take the water, you will get the values of this surface tension value of water is around 72 millinewton per meter or dynes per centimeter. And then if we add more surfactant into the water, then you can see that it will decrease. Say at this point, this is the surface tension value, then this is the surface tension value, then this is the surface tension. We have to prepare the surfactant solution of different concentration, and in this way you will get a plot. And after that, if you draw the plot, and you'll find that at a certain concentration, after a certain concentration, there is no further decrease of surface tension value. So that particular value is known as the critical micelle concentration. Now, this surface tension value basically sometimes, or interfacial tension value sometimes play a important role. That is how it displaces the oil when the oil is trapped within a fine pore. So here you can see that there is a typical problem, that is calculate the threshold pressure necessary to force an oil droplet. Say, for example, this is the oil droplet that is trapped. To force the oil droplet through the pore throats that has a radius of 6.2 micrometer and a rear radius of 15 micrometer, and assuming the wetting phase contact angle is 0 and IFT value is 25 dynes per centimeter. Okay, and you can be asked to answer this question in the both the unit in the dynes per centimeter square and PSI. Both are the unit of pressure, and what would be the pressure gradient if the drop length is 0.1 centimeter. So this is a fundamental equation of the pressure gradient, which is related to the if you go through some standard books, that is the 1 by R2 by 1 by R1, that is PV minus PA, that is equal to 2 into this is the gamma, that is the dynes per centimeter, and 1 by R1 by minus 1 by R2, that values is given in centimeter, and by simple calculation you can get the values in dynes per centimeter. That is that this pressure is required to press the oil through these pore throats, and you can for get it in the PSI, you have to simply use that conversion factor. Now, I just want to say that sometimes what happen, as I mentioned earlier, this if you are this is the viscous force that you have to apply by injected water. Now this there are some interfacial forces there, and if the interfacial tension is basically much higher, then the viscous force may not be sufficient. Okay. So in that case, say if this is the say surface, this is the IFT value. Now, if you reduce the IFT value, you can you should know that you can reduce the IFT value into 10 to the power minus 3 range. Then in that case, this threshold pressure will be much less. Because if it is, you can say that is it is 25, and if it is say 0.025 0.25, so it will be reduced to 1,000 times lower, and then by low viscous force you can displace the oil through the fine throats. In that case, there will be, you can see that there will be deformation of this layer. And for pressure gradient, you can simply get the delta P by L, so that this is the pressure gradient. Now, this capillary number is very, very important in enhanced oil recovery. And we know that capillary number is expressed as this the mu V divided by sigma, and it is basically it is as a ratio, it is the viscous force by capillary by interfacial force. Now, we know that our main objective for chemical enhanced oil recovery is to increase the capillary number. So how can you increase the capillary number? From this equation, you can see that if we increase the values of mu, that is the viscosity of the injected fluid. So how can it be done? You can increase the viscosity of the injected fluid by adding polymer. Then you can increase the velocity, the V, but there is some limitation. You cannot inject, or the velocity should not be very high. In that case, there will be channeling of the injected fluid, and not only that, the contact time between the chemical slug and the formation rock will be less, and then you cannot get the effective recovery. So the most important parameter is that interfacial tension. So you can definitely improve the viscosity, but again, it is not too much, and particularly for the shale and tight reservoir tight formation, because of the injectivity issue, you cannot increase the viscosity too high. So the best option to increase the capillary number is to reduce the interfacial tension. And as I have mentioned, that is, it is possible to reduce the interfacial tension by some value like say 10,000 times, 10,000 times. Okay. Now, from some field data or some experimental data that you can performing some experiment in the laboratory, you can get some idea about the capillary number. What should be the capillary number? I am talking about to increase the capillary number, but at least you should know that what is the values of capillary number, whether it is 100 or 1,000 or 10,000, like this. So then if we go for a typical example, say injected fluid having a viscosity of 10 to the power minus 2 Pascal second, and IFT value of 10 to the power minus millinewton per meter, and it is moving through the formation with a velocity of 7.5 into 10 to the power minus 6 meter per second. So you can see that a velocity is not too high, it is obviously very low. So now it is flowing through the formation, then what should be the capillary number? So we can use that equation, and you can see if we put the values of viscosity here, so it is 0.01 as it is 10 to the minus 2 Pascal second, and IFT value is 10 to the minus 2 millinewton per meter. So for unit consistent, you have to convert it into Newton per meter. So then it is this is the interfacial tension. So it is 0.1 and divided by 1,000 to convert it into Newton per meter. So this is the values of this interfacial tension, and this is the values of the velocity. Then you will get this is the value. So though I am basically telling that increase the capillary number, but still you can see that capillary number is always in the most of the cases less than 0, so less than 1. So here it is, you can see 0.0075. Okay, and here you can see that some typical values of capillary number. If you increase the capillary number, so you can get the improved recovery. Now, I will discuss some core flooding experiments. So, this is, that to get the enhanced oil recovery, first you have to perform the study for using any chemical slug. You have to perform the study in the laboratory by using a core flooding system. So here you can see a typical core flooding system. So core is taken here. Then what are the subsequent steps, or stepwise, what are the steps to complete the experiments? First, you have to measure the porosity of the core. That is, you have to measure the phi value. Then after that, you have to saturate the core with the brine. And then if you put the core here, and this is a typical syringe pump. And then if we inject the brine, and collect the brine from here, and there is a pressure transducer or pressure gauge is there. Then at steady state condition, obviously you should maintain the laminar flow. And if you basically maintain the laminar flow and steady state condition, then you can that how much you can get it from both way, either that what rate you can injecting the brine that you can get from your the system of the displacement pump. There is some meter is there. Otherwise, you can calculate that particular time how much water is collected. So accordingly, you can get the flow rate also. Then, if the flow rate is known, and then the pressure drop around the core is known, then you can get that what is the then if the viscosity of the brine is known, then area of the core, then length of the area means I want to mean the flow area, and length of the core is known. Then using the Darcy's law, you can get the absolute permeability. So this absolute permeability measurement is very important. So based on this experimental study, I will discuss one typical problem. So here the problem is, say, in a core flooding test was conducted in a laboratory with a sandstone core sample, and length of the core is 35 centimeter, and diameter is 3.5 centimeter. That is the dimension of the core is known, and porosity of the core is 22%. That you can measure it by saturation method or any other method. There are so many methods for a measurement of the porosity, like helium porosimeter is there, gas porosimeter is there. That is gas, I want to mean this nitrogen porosimeter is there. Now, for this flooding, initially the core was saturated with the brine and then flooded with the crude oil. The core is first saturated with the brine, and then, as I mentioned, first saturated, and then you can basically further inject the brine to measure the absolute permeability. And after that, on got the values of absolute permeability, then I want to make it, I make to the condition where some initially certain saturation of oil is there. So for that, I have to flood it with the crude oil. Now, during the flooding, during the flooding, during the crude oil flooding, 60 ml of brine was produced. So during the experiment, it has been found when we are basically injecting, first it was saturated with the water, and now we are injecting the oil. Then what happened? This oil will displace the water and it will be collected here. So now you continue to inject crude oil until, so what happened at start, mostly the water will be collected, then after some time you'll get that both crude oil and water is coming out. Then slowly the amount of crude oil at the outlet will be increasing and the water will be decreasing. At some point you'll find that only crude oil is coming out, no water is coming out. Now you have to analyze this collection sample. That is, you have to separate, or you have to allow some time to get it settled, so that you can get that how much volume of water and how much volume of crude oil is there. And according to after that, say it is observed that during the crude oil flooding, 60 ml of the 60 ml 60 ml of the oil was used, and then core was flooded with the brine. Okay, so after that, when your that is the, it is basically after it will find that having some initial oil saturation, and then what happened, we have to check that by water flooding how much crude oil is produced. Then you have to again inject brine. Okay, then brine, what happened, this this brine will displace the oil and the crude oil will be used. And after some time that as you are injecting brine, this crude oil and water both will be produced. Okay, and after at some point you'll find that it is mostly water is coming out, and that actually happens during the water flooding. Sometimes your water cut reaches to the 95%, and this condition, it is really difficult to continue production, because very less amount of oil will be produced, and this treatment of the huge amount of produced water is very difficult. So your process will not be economically viable. So you have to think for other enhanced oil recovery method. So after that, what you have to do, you have to inject the different chemical slug. Either it may be polymer, or it may be surfactant, or it may be the different combination of the, say, alkali surfactant, polymer, etc. And then by the mechanism that is we have already discussed, by reducing the interfacial tension, by improving the sweep efficiency, by changing the wettability of the rock from oil weight to the water weight, by emulsification, we will get the significant additional recovery. So according to this problem, it is observed that that core, when the core was flooded with the brine, then 28 ml of the crude oil is produced. So this crude oil is produced by water flooding, that is by secondary method. And up brine, the system is flooded with the polymer solution, and an additional 15 ml of the water is produced. So from this experimental study, you have to calculate the initial oil saturation. What is the initial oil saturation? What is the irreducible water saturation? What is the oil recovery by water flooding and oil recovery by polymer flooding in terms of percentage of original oil in place. Then the residual oil saturation after water flooding, then residual oil saturation after polymer flooding. So this is the question. You have to solve this problem. So according to the data provided, first is the core length, that is the length is given, then diameter is given. So you can get the bulk volume of the core sample. So this is the bulk volume of the core sample. Then the porosity is known 0.22. So the pore volume is equal to 0.22 and this 336.74. So this is the pore volume. Now the volume of water displaced. So after first study, that is volume of water displaced. So initially it was saturated with the water. Then you are injecting the crude oil. Then the water that is displaced, that is nothing but the volume of oil present in the core initially. So that is we have basically measured as mentioned. It is the 60 ml. Okay. And therefore the initial oil saturation is 60 divided by the pore volume. This is the pore volume, that is the 74.0828. So you can see that initial oil saturation is around 81%. And what is the irreducible water saturation? So it is nothing but 1 minus SY. So that is equal to 19%. Then water flooding. So by water flooding, volume of oil initially present in the core model is 60 and 60, and the volume of oil collected is equal to 28 ml. Therefore, the secondary recovery that is equal to 28 divided by the original oil in place was 60 ml, sent here. So divided by 60, and if we convert into percentage, so this is 46.67% of original oil in place. So this is the recovery by water flooding, by secondary oil recovery. Okay, that is around 46 or 47%. So next, so obviously you can see that this value is not satisfactory, because in this study it's performed in the sand pack, and our objective is so around 54% oil is still there. So let us try for chemical flooding. Now with this polymer injection, it will be polymer flooding, not the surfactant in this particular problem. So additional 15 ml of water is produced. So and 15 ml produced. So additional recovery. So this is the 15 divided by the original oil in place and percent. So it is around 25%. And Therefore, the total recovery is your secondary recovery plus, so it is 71.67% of original oil in place. And then you can get the residual oil saturation after water flooding. So that is residual oil saturation. So originally it was the 60, then 28 ml is produced by this water flooding, and therefore after water flooding, if you was the oil remaining and divided by the this pore volume, that is the pore volume. So this is the saturation. It is the 43.1%, 19%, and this will be polymer here in this particular problem. So this is after tertiary recovery. So originally it was 60, then this is produced by water flooding, this is produced by polymer flooding, and this is the pore volume. So it is 22.93. So you can see that this residual oil saturation after water flooding, it was around 43 percentage, and then after this tertiary recovery, it is reduced to around 23%. So this is a typical problem for polymer flooding. The same type of the problem you'll get if you go for some study with the surfactant, with the alkali, or a combination of the surfactant and polymer, etc. And obviously, when what is the mechanism here, why you are getting this additional recovery? So additional recovery you are getting is by improvement of the improvement of the sweep efficiency, and then if you use the surfactant, you will find that what is the recovery that you are getting, that is basically improvement of the displacement efficiency. And if we use the both surfactant and polymer, so in that case, there is some reported study that you can get it more than 90%, more than 90%. Okay. But the design, that is the injection mode, and the composition. So there are so many parameters are there, and you have to design it perfectly in the laboratory. And then if you think that the recovery is significant, then you can go for the pilot study. And if it is again successful in the pilot study, then you can go for the field application. So these are the the plot for this polymer flooding of different concentrations. So you can see that this is the recovery by water flooding. So after a certain pore volume injection, it is there is no further recovery, and then you are injecting this polymer, then followed by chase water. Is the polymer minded this polymer or this surfactant? These are not continuously injected, only a certain pore volume, maybe 1 pore volume or 1.5 pore volume, or sometime less than 1 pore volume may be injected, followed by to get the just to form the oil bank by mobilizing the trapped oil. And after that, if you basically inject the chase water to maintain the pressure, so that this polymer slug basically move forward and displace the remaining oil. And then you can see there is significant additional oil recovery. Okay, and then what should be the concentration of the polymer? Then you can perform some study, and then you have to optimize, because you may get some marginal increase in recovery by increasing the concentration of the polymer, but at the same time your cost of the polymer will be increased significantly, and that will basically hamper or basically increase the project cost. So you have to take the certain decision that what polymer should be is, and generally it is in the field around 1,000 to 1,500 ppm of the polymer solution is generally injected. So here these values are given here, the different parameter that this is the porosity, this is the permeability at initial, that is the when SW equal to 1, and this is the relative permeability to permeability to oil at initial water saturation, and these are the this composition of the polymer. There are 4 different type of study was performed here by injecting different concentration. So this is the recovery. This is some other data it is taken, not from this particular problem. And this is the addition. So you can see that after say 2000 ppm, the increase in recovery is not significant. So so you can consider that 2000 ppm is the optimum concentration. Now for surfactant, there are Jeff mentioned that is the surfactant very importantly form the emulsion, and this emulsion, particularly the micro emulsion, is a very important mechanism to improve the recovery by lowering the interfacial tension. Now, how these emulsions are formed? For these emulsions are basically mixture of 2 immiscible liquids where one phase is dispersed into other phase. So for this particular field, the different component of the emulsions are the surfactant.
Sir, I have one question.
And then oil and the brine. So there are 3 component system is there, and depending on the types, there are different types. Also, first is that Windsor type 1. So what is the Windsor type 1? This is the Windsor type 1 where this is the micro emulsion, the bottom, and there is some excess oil at the top. So what is the micro emulsion? So micro emulsion is a continuous water phase and oil is dispersed here. Then Windsor type 2. Windsor type 2 is this is the micro emulsion is the at the top, but here you can see that water is dispersed into the oil. Okay.
Sir, I have one question. Like, is
This
there
water
any
bottom.
analytical equation?
And there is another type is known as the Windsor type 3 or middle phase micro emulsion. So here you will get excess oil and excess water at the bottom, and this micro emulsion at the middle. So this particular type 3 micro emulsion is actually very useful for enhanced. See that one side it is the oil and the other side it is water. So it is having the miscibility both with the oil and water, and provides an ultra low tension. Now in the micro emulsion, what is there? In the micro emulsion, there is water is there, oil is there, and surfactant is there. So based on that, there is one parameter that is called solubilization parameter of the oil. Solubilization parameter of the oil. So it means how much volume of oil is there in the micro emulsion and how much volume of the surfactant is there. And then solubilization parameter water means how much volume of water is there, how much volume of surfactant is there. Okay. Now this can be printed by material. We'll see. Now there are some typical middle phase micro emulsion. It depends on the so many parameters like salinity, temperature, etc. not going into details. So here you can see some typical study that was conducted in our laboratory. So here it is the basically middle phase microemulsion. And here you can see that this solubilization parameter, there are two types of solubilization parameter. One is the solubilization parameter, and this solubilization parameter oil. So it is basically plotted versus salinity of the system, and then you will get the two different plots, and they will intersect at this point, and this is known as the optimum salinity. And it has been observed that optimum salinity minimum active. So this salinity is good designing the injected substance. This interfacial tension for this microemulsion can be calculated by this very important equation, that is Chun-Hui equation. So interfacial tension equal to C by the solubilization parameter square. Okay. Now the solubilization parameter, as I mentioned, you can get it from this material balance. And then if these values are known, and the values of C, it is generally for typical crude oil and surfactant system, it is 0.3 millinewton per meter. And then you can get the IFT values. So now if we go a typical question, say around 6 ml of oil and 6 ml of brine solution were mixed in presence of 0.05 ml of surfactant liquid. Okay, a three-phase microemulsion form with basically 3 ml is the upper oil phase, 4.5 is the middle phase microemulsion, and 4.5 is the lower phase microemulsion, more lower phase water. So determine, you can get the two IFT values, okay? Two IFT values. So according to this previous equation, so you are getting this solubilization parameter, okay? So first is the oil solubilization parameter. So it means how much oil is there in the microemulsion. So you can get the by material balance, the oil solubilized in microemulsion is equal to 3. And we are assuming here that most of the surfactant is present in the middle phase microemulsion. So divided by this is the volume of the surfactant. So this solubilization parameter value is the 60. And water solubilization parameter, similarly, it is the 30. And therefore, oil water emulsion, the IFT value is equal to 0.3 solubilization parameter. So 8.3 into 10 to the power minus millinewton per meter. And at water emulsion interface, it is the 3.3 10 to the power 4 millinewton per meter. And if we basically at optimum salinity condition, as I mentioned, so at optimum salinity condition, generally it's observed that both the IFT values are same. So thank you. This is the some input about the fundamental, that is the numericals, that is very much useful for this surfactant or polymer injection. Okay, thank you.